Hi again. Last time we defined what a determinant is, and we were able to find the determinant of a matrix using the cofactor expansion method. For this lesson, we are going to study the effect of elementary row operations as well as elementary column operations on the determinant of a matrix, and also determine the conditions that make the determinant of a matrix 0. Okay, so we will have determinants and elementary operations. The objectives for this lesson: at the end of the study, you should be able to use elementary row operations to evaluate a determinant. Use elementary column operations to evaluate the determinant and to recognize conditions that yield 0 determinant. Okay, beginning with the effect of elementary row operations and on the determinant of a matrix. Theorem 3.3 tells us about the elementary row operations and determinants. Let A and B be square matrices. When B is obtained from A by interchanging two rows of A, then the determinant of B is the negative determinant of A. When B is obtained from A by adding a multiple of a row to another row of A, then the determinant of B is just the same as the determinant of A. Meaning, adding a multiple of a row to another row of A does not change the determinant of the matrix. In number 3, when B is obtained from A by multiplying a row of A by a non-zero constant C, then the determinant of matrix B will be equal to C times the determinant of A. Okay, let us have this example. Find the determinant using elementary row operations. We have A, which is a 3 by 3 matrix, and the following entries. You have 0, negative 7, 14, 1, 2, negative 2, 0, 3, and negative 8. Last time, we learned that the determinant of a triangular matrix is simply the product of the diagonal entries. Now, taking a look at column 1, since we don't have a leading 1, we can try, however, to interchange the rows or interchange row 1 with row 2 so that we can have a leading 1. Okay, so let's say we interchange the first two rows so that the resulting matrix will have the leading 1, and then you have 2, negative 2, 0, negative 7, 14, 0, 3, negative 8. Now, since we interchange the first two rows, then the resulting determinant will be negative. Now, since we already have a 1, 0, 0, the next thing to do in order to convert this to a triangular matrix is to make a negative 7 equivalent to 1 and 3, 0. So we need to perform additional elementary row operations, right? Now, taking a look at row 2, we see that the entries are simply divisible by negative 7. So if we factor out negative 7 from row 2, then the entry will become 1 and negative 2. Okay, so that we will have it here. So factoring out negative 7, and remember that the initial sign is negative, and then factoring out a negative 7, this results to a positive 7, and then we will have the new matrix. So you already have 1, 0, 0, 1. And the next thing is to make this 0 so that we can already have a triangular matrix. And now we are ready to convert 3 to 0 by simply multiplying. Okay, let's say we multiply row 2 by negative 3 and add that to row 3 so that we will have, say, negative 3 times 1 is negative 3 plus 3 is 0. And then negative 3 times negative 2 is positive 6. 6 plus negative 8 is negative 2. So now we will have a triangular matrix whose diagonal entries are 1, 1, and negative 2. So the determinant of this matrix is simply 7 multiplied by the diagonal, the product of the diagonal entries, 1 times negative 2, which is all equivalent to negative 14. Okay, so just like we have an elementary row operation, we can also have what you call elementary column operations. So operations performed on the columns rather than on the rows of a matrix are called elementary column operations. And two matrices are said to be column equivalent when one can be obtained from the other by elementary column operations. Okay? In example number 3, we're asked to find the determinant using elementary column operations. Now, A is also a 3 by 3 matrix, and notice that the first two columns of A are simply multiples of each other. So you can obtain a column of zeros. If I multiply column 1 by 2 and add it with column 2, that means 2 times column 1 and add it with entries of column 2 to be the new column 2, then we will have, okay, this is the new column 2. We ended up with a column of zeros. Okay, now if you're going to perform a cofactor expansion on column 2, we will see that the determinant is 0, right? Because remember, for a cofactor expansion, we will have an aij multiplied by a cofactor ij. Now, since all aij's here are 0, then the determinant of this column, the determinant of matrix A in this problem is equivalent to 0. So say 0 times cofactor 12 plus 0 times cofactor 22 plus 0 C32 cofactor 32 is 0. Now, what about zero determinant? What are conditions that makes the determinant of a matrix 0? Okay, according to, theorem 3.4 gives us conditions that yield a 0 determinant. So if A is a square matrix and any one of the conditions below is true, then the determinant of A is 0. First, the determinant of matrix A is 0 when an entire row or an entire column consists of zeros, or two rows or columns are equal, or one row or column is a multiple of another column. For example, A is said to be a matrix with 0 determinant. Now let's see why. Adding negative 2 times the first row to the second row produces the following. Okay, so we will have negative 2 times 1 is negative 2 plus 2. We will have 0. Okay, and then again, negative 2 times 4 is negative 8. Negative 8 plus negative 1 is negative 9. And negative 2 times 1 is negative 2 plus 0 is negative 2. So we already have a 1, 0, 0. Okay. Now, take note that the second and third rows are multiples of each other. So the determinant is 0. Because if we multiply row 2 by 2, and add it to the entries of row 3 to form our new row 3, row 3 will eventually be 0. Okay? And according to the theorem, a matrix that contains a row of zeros will have a determinant equal to 0. Okay, so for today, we were able to use elementary row operation as well as elementary column operation to determine the determinant of a matrix. So in the next lesson, we will be discussing the properties of determinants. I'll see you next. Bye.